Again, I would like to introduce our speaker for tonight, Professor Francis Bretherton, the same uh, speaker we had last time. And today's topic is hydrology and the hydrological cycle. And I'm sure you will have questions at the end, and please do ask them at the end because I think that's the part that makes the live lecture that much interesting. So without any further delay, here's Francis.
Thank you, Sanjay. I'm Francis Bretherton. A couple of changes in technique since last week. On the images you have in front of you, but alas, not the image I have here, you will see at the bottom of the beginning slide is a comment that if an image is too small to read and you click on it on the website, you will get an enlarged version. So you're very much encouraged to go to the website to get the slides for this, because I recognize that you won't be able to read the type on these slides, but it is there in that way. Now, today's lecture, if I can get to it, and excuse me, I've got to learn how to press these buttons in a hurry when I need to. Okay. Today's lecture is on water, and the correct title is Why is Water So Important? I noticed my chagrin that I picked up not the final version of this talk when I came today, so you're going to have to bear with that. The website and the version I hope you have has the so important rather than so controversial. Now, of course, I'm pressing the wrong button. There's a whole set of questions that we need to address in relation to water. The first, of course, is how much water there is. A second one is how we use it, in particular the distinction between surface water and groundwater. We also have to discuss pollution and essentially the issues associated with managing the water supply. Now, to start, we take a look at the hydrologic cycle as a whole. This diagram is a little bit complicated. Can you see that mouse on the screen?
Yes.
You probably cannot read the subtitles. I apologize for that. But I'm going to explain roughly what's here. The hydrologic cycle starts when water evaporates primarily from the surface of the ocean, condenses in the atmosphere and comes down as precipitation. That's either rain or snow. It runs off down the surface or it infiltrates into the ground as groundwater. And that groundwater also flows downhill into lakes or rivers or streams. Some of it's picked up by plants through their roots and evaporates back to the atmosphere. We call that transpiration rather than evaporation. And others of that flows down rivers ultimately into the ocean. And on that way down, either in the lakes or the rivers, it's really available to humans for our use. Whoops, I clicked the wrong button here. I apologize. I've got to get back from that. No. Okay. Now, let's first think where the water actually is. And of course, the vast bulk of it is in the oceans. In fact, this quotation from the ancient mariner, "Water, water everywhere, nor any drop to drink," reminds us, of course, that the water in the ocean is salt. We humans have the have in our system the fact that we need fresh water rather than salt water. we can't use that salt water. And land plants, likewise, are poisoned by too much salt, which becomes a real issue in terms of the quality of fresh water that we can use. Now, most of the fresh water in the world is locked up in ice sheets and glaciers. Even that's only a little less than 2% of the total water available in the system. Unfortunately, most of it is in fact too difficult for us to get to. About 0.5% or so of the total water supply is in groundwater. This is someone just simply examining a spring underneath a slope. The water that is under there is basically in the pore crevices in the soil and is known as groundwater. A still smaller fraction is in lakes and rivers, like this lake in northern Wisconsin, and only 0.001% is in the place that we most think of, namely the atmosphere. This picture of the thundercloud, of course, was taken by my son. That's why I put it on here, to do a little bit of advertising. But let's move on now to the next topic, which is on how we use surface water. And most of that surface water we use is basically river flow. River flow, of course, is flowing down streams and rivers. And this is an image of a gauging station. This particular one happens to be in a mountain gorge on the island of Cyprus. The gauging station is part of the World Hydrological Cycle Observing Network under the auspices of the World Meteorological Organization. In this picture, what you see is the guts of the gauging station is down here where the mouse is, and basically it's just a fixed shape of concrete that the water runs over. And on the far side of it is what's called a stilling well that's connected by a pipe to the stream as a whole, and the water rises in the stilling well to a measurable depth. And it's from that depth that one can calculate, given the shape of the sill over which it's flowing, what the actual flow rate is in cubic feet per second. That is then radioed in, telemetered either to a satellite or through a cell telephone or through a landline link into a central analysis station. And that's where we get all our information about water. This particular slide here shows the daily river flow. This particular date is March the 9th. I downloaded it a week ago. I might just as well have done it today, and you would have got a picture that looked very similar to this. Again, the details don't matter. Every dot on this image is in fact a gauging station in the US, and it's color-coded such that the red dots are areas where the stream flow is very low, abnormally low. The blue and the green are such where it is wet. And so you see right away from this map that at this time, last week at least, there was a drought in the southeastern United States, showing up very clearly in the stream flow there. Now, that water from streams is widely used in irrigation. This particular image is from Imperial Valley in California. And that water is being used to irrigate a field of, I'm not sure what, they look like they're soybeans or something like that. It's, of course, a little bit amusing that water, in fact, comes from the Colorado River, but it's worth noting, if you look at the map, where the Colorado River actually flows into the Gulf of Mexico, or nominally does, it's at least 150 miles east of this point. And in fact, that water is drawn in a canal all the way across Southern California. And when the Colorado River flooded about 50 years ago, it diverted down that canal. and filled up what is now the Salton Sea, a large body of water just next in Imperial Valley. It's steadily drying up. We hope that refilling of the Salton Sea doesn't happen again. Lost it. Here we are. This is another image of another use for water, and that's for generating hydroelectricity. This is the Hoover Dam on the Colorado River, and this outlet here is out of the hydroelectric station. There, of course, is the dam in the back, and the difference between there and there is the head, the difference in height down which the water flows to generate the electricity. Yet another use of surface water is for cooling. This case, 3 Mile Island Nuclear Power Station that you've probably heard of. The cooling water goes into these cooling towers. Some of it evaporates. Most of it is fed back into the river from which it came, and which basically it is recycled. Unfortunately, when it goes back into the river, it is warmer than when taken out, because of course it's cooling things, and that gives rise to an issue of water quality, particularly in summertime, that the fish and things like that may not like it that warm. Now, another topic, of course, is using groundwater. In particular, the water of which we saw flows under this ground. And this diagram here, I'm going to have to walk you through a little bit, shows the principles of that. As I mentioned before, if you go to the website and click on this image, you can get a real full-scale version in which you will be able to read everything and print it out to as much as you like in order to be able to reuse this in other contexts if you wish. I got this diagram from the United States Geological website, Geological Survey website. It's public domain and feel very free to use it. I found it actually a very useful sequence of diagrams, and I'm going to follow them for the next few minutes to explain some of the principles for groundwater flow. It starts, as I mentioned before, with rain falling from the sky onto the soil, and some of that rain, most of it, infiltrates in through the surface layers of soil, through the porous cavities. And it essentially drops down until it comes to a level at which the pores are saturated with water. That level is called the water table. Notice at the bottom of this layer of saturated soil is a rock, solid rock or clay underlying surface, which is not porous, and that confines the water flow between the water table and the confining unit. And basically it flows like a river down the slope of the water table. It's a pressure gradient forcing it through the pores in the rock. Unlike a river that flows at several feet a second, this water flow is at millimeters a second, very slow on the average. It creeps through there. But some of it creeps through directly as groundwater, directly into a stream. And that's one of the ways stream volume and river volume is maintained, is in fact inflow from groundwater. Now, what happens if you drill a well? Drill a well in the middle of this here and pump water out of that well. What this diagram shows very clearly is that in the vicinity of that well, the water table drops rapidly. If you weren't pumping, you can measure the height of the water table by letting the water in the well come to an equilibrium position, measuring what it is. But that's only when you're not pumping. If you are pumping, the water table drops. And notice something else that happens, and that is the stream flow from, or the water flow in this direction is down the slope of the water table, and it's now, instead of from the groundwater into the stream, it's from the stream into the groundwater. That, of course, is very important because most people don't think of that reverse flow, and are then surprised when stuff that gets dumped in that stream ends up in their well, at which point they are very annoyed. But let's see how groundwater is actually used. This image here is showing, there's two. The satellite image at the top shows these red circles. Now, they're not really red, they're green. Red is a false color which is used by the satellite operators to make the images easier to read. You've probably seen circles like this when you have been flying by airplane over, for example, Nebraska, western Kansas, eastern Colorado. You can see quite a number of those circles looking down from the air. They're the signature of a technique called center pivot irrigation. If you look down on the ground beneath that satellite image, you will see what is really giving rise to those circles. What you see is a little gantry with wheels, and it's a giant sprinkler system. One end of that gantry is attached to a pivot at the center of each one of those circles. And when the sprinkler is operating, it moves around that pivot and essentially covers the whole area of that circle. Now that circle is about 1/4 mile across. So this is a long gantry. When they're operating, pumping water, there's a great big spray that is quite spectacular. In fact, you might like to find some of those around Wisconsin. I know of at least 4 or 5 in the Madison area that I've noted by the side of the road. I haven't seen them operate very much, but basically what they are doing is pumping water up from the aquifer below, from below the water table, and putting it through a high pressure nozzle and distributing it then all the way over those red fields. And that is what's going on. These images, by the way, these Landsat images are obtained from a website. There's a beautiful set there. It's at the Eros data center. And if you want the URL for that, just click on the caption here on the website, and you will get that information. This picture here is another satellite image taken from Saudi Arabia. An unlikely place, you might say, for irrigated lands and a city, which is in fact entirely new in the last 20 years. The development of that city, which is this area here, is clearly associated with the simultaneous development of center pivot irrigation in the vicinity. It's basically that what enables the Saudi population to live in that part of the world. Unfortunately, there's a catch. As I said, these are drawing on an underground aquifer and they're pumping the water out, and it's not being renewed anything like as fast as it's been pumping. And the water table is dropping. Basically, they are mining that aquifer. And the same is happening in the United States. We'll come back to an example of that in a little, of that mining going on. Before we do that, I want to quickly take you down one of the consequences of a falling water table and of the well diagram. On this diagram you have in front of you, and that's strange because I don't have it in front of me. Why? I must have an old version here. I have a different diagram in front of me. So the one that I'm showing on your screen does have the feature I'm looking for. As you see here, that a little bit of blue, you may not be able to make out all the detail, is in fact the signature of pollution, polluted water that got in at the surface up there. And this diagram shows it essentially flowing down into the water table, downhill into, guess where? Your favorite well site. Those well sites act as a magnet for all the pollution around, coming from the surface water there or for those streams. We should not be surprised when we dig a deep, high-volume well and pump out of it that we end up collecting a lot of the pollution that's already going on in the area. This, of course, is a major current issue in Wisconsin of water use management. I'm sure you've heard about this in the press. Another case study I want to take is the so-called Ogallala Aquifer that stretches all the way from South Dakota to Texas. It is a fossil aquifer in that it recharges, but relatively slowly. Since in 1920, the average thickness of that aquifer was 20 meters. It is now 4 meters. That's the thickness of the saturated layer of water from which everything is coming. This map here of the aquifer as a whole, in the north here is Nebraska, the southern end of here is southern Texas. The red and yellow areas are the areas in which between 1990 and 1980 and 1994, a 15-year period of which these measurements were taken. The area of water there, the depth of the water table in the red and yellow areas declined dramatically. And essentially the farmers who are depending on that for their irrigation water, for their center-pivot irrigation, for their livelihood, are almost out of luck. Because by 2020 or so, at the present rates, that aquifer will be exhausted in those areas. Now, what this data interestingly shows is in the extreme north and the extreme south, over that 15-year period, the depth of water actually increased a bit. That's the good news. The bad news is that when you look at the rainfall for that period, you find that immediately preceding this, the end of this period, was 2 years of abnormally high rainfall. And it's probable what we're seeing here is the apparent health of the aquifer north and south is a short-term fluctuation rather than a long-term phenomenon. But this is typical for the sorts of problems that are arising with groundwater being used extensively for irrigation. Let me change the subject yet again to pollution of rivers and wells. Here is the better example of what I was trying to show earlier, and I apologize. I got the sequence confused here. This area of blue, now here's my mouse. Can you see that? This area of blue here is the polluted water, heading right down into the well. And you also notice, again, water coming in from the stream into the well. Both those are potential sources of pollution. Now, the United States Geological Survey is taking this very seriously. This map here shows Wisconsin, Iowa, northern Illinois, and of course Lake Michigan here along to the right. The red dots and blue dots are wells that have been surveyed for whether they have measurable pollution in them, in particular evidence derivative products of herbicides, essentially runoff from fields, cultivated fields above. Notice your area in northern Wisconsin essentially was not tested very much. But over the rest of this area, it's disturbing to note that about 30 to 40% of the wells surveyed had measurable amounts of pesticides in them. That does not mean those wells are dangerous for drinking, because there will be no standard set by the Environmental Protection Agency about what is safe. This was simply, survey was not to establish what was safe and what was not. It was to establish a baseline so that by coming back and measuring in another 10 years or 20 years, they can actually say how much better or worse things actually are. That's a different purpose, so don't get unduly alarmed by this. But nevertheless, it shows that 40% of shallow wells are in fact already polluted in the upper Midwest. Now, most of our drinking water comes from these groundwater wells. In rural areas, they're shallow. Urban areas like Madison get their water from a much deeper aquifer, more than 1,000 feet down, and that is less, at this time, less liable to pollution. When the water gets down there, of course, it'll be a disaster. Now, there's another issue of pollution. This particular picture is, in fact, from an abattoir, a slaughterhouse, and the effluent from that abattoir is just getting into an open drain and going into the nearest stream. This particular picture was actually taken from South Africa. It's not a US example. I want to indicate that this is a worldwide problem. But fundamentally, this pollutes the drinking water sources for most of the world's population, are in fact don't have the benefit of pure water the way we are used to, and in fact live with polluted water, and it is the major source of disease for the population of the world worldwide. Now, what can be done about managing the water supply? This is inevitably a very general statement, and I'm just going to illustrate some of the principles. We have to remember that usable water is limited by the amount available for precipitation, primarily. The groundwater for irrigation, as we've seen, is rapidly exhausted in the places where it is most needed. Only where there's plentiful rainfall is it being recharged at a rate that really makes it a renewable resource. And in those cases, it is usually easier to take the water from streams and rivers than it is from the underground aquifers. So in the large-scale picture, in the arid regions where it is most important, you've only got surface water as your real resource. And it's worth noting that most of the water in those areas re-evaporates from vegetation and reservoirs before it gets down the ocean. That is saying that one way or another, that water is all being used. And the last point that I would like to make, we started off this survey with a view of the ocean. There's plenty of water in the ocean. The problem is getting the salt out is extremely expensive. It uses lots of fuel to do it. It's energetically expensive. And the impact of that, of course, is that it is only used when there is nothing else. In terms of water management issues, we need to reflect that probably we have a very distorted idea of what water costs. Yeah, I know we pay the charges on our water bill each month. That is a small fraction of the real costs of water. And what this slide does is to try and draw your attention to what some of those real costs actually are. The ones you tend to pay for are those for extraction and treatment, the immediate cost associated with that. But the environmental cost, the cost, for example, of depriving the natural vegetation of that water, they're not counted in there. The health costs of the water being polluted is not in there. And we simply have a false impression that water is cheap and always available. Most of the world, tain't true. If you go out in the Western United States, it's certainly not true. Every resident of the West is very familiar with the fact that water for human use is a real issue that limits the economic development, in fact, the population of those states. And government subsidies have traditionally used to develop water supplies. The Hoover Dam, for example, was built entirely on federal funds, and the water is sold to farmers at a fraction of the real costs of that operation. Why? Well, agriculture is valuable production. But when water is in scarce supply, we really have to develop better mechanisms for balancing the competing needs on it, because there's only a finite amount available, and it is a continuous source of friction. What, in fact, can we do? How can we make more effective use of this? Well, we can use water. First thing we can do is try and conserve it. That means changing our irrigation practices. Agriculture, as I said, is far the largest water consumer. There are much more efficient ways, like drip irrigation, uses less water than spraying on the field from center pivot, or worst of all, doing what you saw in Imperial Valley. That's an extremely wasteful use of water, and if there's any salt in that water at all, and there is in the Colorado River, it basically poisons the soil on which it's going, a real issue. We can learn to recycle water. Now, in urban areas, what goes down the storm drains goes right into the nearest stream. If you've flushed out your engine oil from your car, and that goes down a storm drain, a frequent occurrence, you are basically polluting someone's drinking water. And that's a serious issue. The runoff from storm drains is not good, either for a river or for well water drinking. We have to control our pollution in the sense of sewage treatments. You can do much better than the standard two-stage sewer treatment, put in tertiary things. Yes, they're expensive. But if you take into account the reuse of that water down the river for other people's drinking, that is enabled by putting that tertiary supply in, that tertiary treatment in, it's very often worth it. We have no mechanisms, no legal mechanisms, to actually encourage this sort of trade-off. And to do that, we simply have to trade the water laws. This picture is a reminder again of the global scheme of things. And just a moment, I haven't got it. It's a map of the world. And you can see marked in brown or red are the countries in the world where they are using, extracting, applying 40% or more of the potentially available water supply, in other words, the rainfall. The yellow, the brown areas, that's 20 to 40%. And the ones that aren't colored basically have got relatively plenty of water. They're only using 10%. Now, this is a crude measure. It's compiled with internationally available statistics on a country-by-country basis, and you see right away it does not distinguish the eastern half of the United States from the western half, nor, for that matter, the eastern half of China from the western half, and they have exactly the same problem the United States does for water availability. However, what I would draw your attention to is where the countries of the world are, and which are already thoroughly committed for all their available water. And now perhaps you understand why President Clinton is spending so much time in that region at this moment. Because this is indeed a really controversial effort. And I suggest that we pause in a moment and discuss what I'm talking. And just for the sake of getting the ball rolling, I propose two questions. First of all, if you were President of the United States and responsible for foreign policy, what would you do about water? And secondly, what could you do in your own community to preserve your water supply? Do you want?
Sure. While you folks ponder responses to that question, I just have a couple of comments. I'm not sure if you read in the newspaper yesterday that President Clinton indeed was in Bangladesh yesterday, and today he's in India, and water is a serious issue in both those countries. But there's something I wanted to add here regarding Bangladesh. As you know, Bangladesh basically is a country that's essentially settled on a river delta, the Ganges and the Yamuna River. So it has a tendency to get flooded every hurricane season. And because it's such a low-lying country, there's extensive flooding and a lot of damage. Some years back, in order to reduce the extent of diseases after a flood, which basically contaminates all of the drinking water, some of the world agencies had given loans to Bangladesh to dig wells for drinking water supply. I think this happened about 20 years ago. And it turned out that in the last 5 years, people slowly discovered that most people were slowly getting poisoned due to the high arsenic content of the water that was pumped up from those wells. So here we have a situation where even though the intent was good, the net result was disastrous. And the choice is between whether you want to die of disease immediately after a flood or whether you want to die a painful death slowly through arsenic poisoning. This is still a question that remains. Most people are still drinking the well water because they have no other source of water, and that poisoning is still going on. So that was just one comment regarding the water in Bangladesh. And are there any questions at the other end there?
Have you comments now from Warsaw? We can't hear you.
One useful way to frame this, which I might suggest for your classes, is I think this is an excellent way to initiate a discussion in your classrooms with the students. We all know that students are, of course, always somewhat enamored with the concept of the power of being the president. And I think it's a good way to introduce not only the idea that water management is a very important societal issue, but it also encourages them to take into consideration their conceptual knowledge base of what they're learning in the course of their classes. And so if I were to utilize this in my, for example, middle school classroom, I would pose this as an end activity that they could conduct as a group and bring together 5 to 10 students in a group to develop a policy paper on water management, either locally or in a selected region in the world that they could study also as part of a history course, for example, or their geography class as well. So this could be a very interdisciplinary type activity. And I just wanted to throw this in to give you a feel for how we utilize these questions when we go into classrooms throughout the state. And so with that, why don't you think in terms, put on your teacher hat and think in terms of how you would use this in your classroom?
Let me just add something to that, and that is that in the last few months there has been a proposal from a company, the Perrier company, to bottle drinking water from some supplies in Wisconsin, and at least in the Madison papers, there have been quite a few stories about some of the issues raised with that. And I think that bottling issue basically addresses some of the same, or it's relevant to the discussion we just had today. But in your classroom discussion, it might be useful to focus on a nearby supply of fresh water, spring water, and perhaps use that as a topic of discussion.
This is Tom in Wausau. Today, my class spent some considerable, considerable time talking about the frog population that seems to be declining over in Minnesota. We had connected to several internet links and taken a look at what they were finding connected to water pollution specifically. We then connected that to what if it were happening in our area and it got into groundwater, and just did a survey of how many students in our classes had wells that they used to drink from at home. It brought a heightened sense of urgency to some of these. And now what the students are doing is tomorrow they're supposed to come back with 3 issues to talk about specifically related to the whole idea of water pollution and what we need to be about. We also are doing a survey of how many of our storm sewers in the city of Merrill actually have painted. There was a group that went around and painted on each of them. This sewer empties directly into the river to try and get people aware. You don't want to put things down here.
Well, I'm fascinated to hear that. We've just had 2 very real stories indicating, in fact, many of the issues I was talking about. I have to apologize a little bit in that I am well aware of the importance of flood control as a water management issue too. In trying to cut this talk down to a suitable length, I decided to leave that out, but I stand corrected about that.
There's one other program that I'd like to just mention, and we conduct training workshops for this, and this is the GLOBE program. I don't know how many of you are familiar with that, Global Learning and Observations to Benefit the Environment. If you have heard that, raise your hand. But you might want to take a look at this particular website. It's, if you just want to write it down, it's very easy, www.globe, lowercase, just the word, .gov, G-O-V. But that particular protocol has a very nice set of activities that you can conduct in any local body of water around your school. And they specifically look at the oxygen content of the water, salinity, which, as Professor Bretherton mentioned, is very toxic if there's a lot of salt in the water, nitrates, which of course are from runoff in agricultural areas, which may be a significant issue in that region, the alkalinity, and of course the conductivity, which tells you how many solid particles are suspended in the water. And so this would be a very nice protocol to take a look at as you're conducting this particular series of sessions in your classroom. So you may want to take a look at that particular site.
And there's also a link to the GLOBE program from our site at www.accc.west.edu/outreach. So if you get to the GetWise homepage, there are links to that.
Oops.
I have a question for the professor.
Mm-hmm.
There was an article in a local newspaper here recently about a tanker going into Lake Michigan and loading up with fresh water and heading back to the Middle East. Are you aware of any of this activity, or?
I wasn't aware of that particular one. I'm not totally surprised. Tankers, of course, have to, in order to be seaworthy, they need their tanks full, not empty. And traditionally, they fill up with seawater. And so the opportunity maybe to make a buck in the process of exporting water to the Middle East, a target of opportunity, I can well believe it. Now, there are some other statistics about international trade in water that you might not know. That, for example, during the 19th century, the major export from Boston, the port of Boston in the United States, to India was ice. They filled their holds up with ice in New England, and essentially by the time they got to India, a good deal of it had melted, but nevertheless the rest of it could be sold at a real premium before the days of refrigeration. A few years ago, about 20 years ago, the time of the first oil shocks, when the Arab countries, the oil-producing countries, and they're not all Arab, were trying to think what to do with their newfound wealth, there were a number of projects to go hijack icebergs in Antarctica and tow them all the way to the Middle East. It turned out that that's no longer really a very economic way of doing it. It is actually cheaper to put in desalination equipment. But nevertheless, there are a lot of sidelights on water because it is a universally needed commodity.
Talking about desalination, is it the energy cost? Is that the main problem? Cost of heating the water?
But it's basically that, yes. You have to evaporate the water, and that costs a lot of energy in terms of latent heat of vaporization. You can recover some of that heat when you condense it back again, but it's not a very efficient process, and it needs a lot of energy to do it.
I just had a quick comment about that tanker filling up with water from Lake Michigan. I think frequently oil tankers do take on seawater or lake water just to clean out their tanks. And in fact, this is one major source of pollution in the open oceans. And almost every tanker that goes out is usually guilty of dumping their wastewater after cleaning out their tanks. And if you go to, especially in the other parts of the world, and you go to the beaches, you'll frequently find evidence of that, in that you'll find clumps of oil on the beaches, almost in any part of the world.
Camera keeps panning off.
Any other comments or questions? If not, I have one. How many of you have been to the Grand Coulee Dam area in eastern Washington? Okay, now there's a story related to the seepage of water through the ground and the effects the water table has on the surrounding area. I happened to be there last summer, and I was there for a different reason, in that downstream of the river, there's an area called Dry Falls, which has a landscape that bears a great deal of resemblance to Mars. But I found out that while we were visiting the Grand Coulee Dam, that once they built the new generator to basically power Seattle, they were generating extra power. There was so much runoff from the dam that overnight that water would seep through the channels away from the canal underground, sideways, and basically raise the level. And then in the morning, when it had drained off, it would seep back. And that started to basically affect the houses in the company town. So much so that the entire town was sinking. So they ended up pumping, I don't know how many millions of gallons of grout to prevent the ground from being affected by this overnight cycle of flooding from the power being generated to supply Seattle. And the comment was that if it would have been cheaper to basically buy every house in that town and displace the people than to actually pump the grout underground.
Other questions? We are probably about to lose our link in a minute or so,